here we have a function that has 3 inputs and then it has 2 outputs. Maybe just to keep them straight, I'll call this first output u and the second output v. And we want to find the change in the output, right, which would be the change in the individual outputs, so change in u and change in v. And now, since we have 2 outputs, we know there have to be 2 rows in our derivative matrix, and there have to be 3 columns because we have 3 inputs. So we could consider a change in the first input, the second input, or the third input. Now, the derivative for the first input, the derivative with respect to u is 3x squared. The derivative with respect to y is 1, so that should be multiplying the change in y. And the derivative with respect to z is negative 2z, so that should be multiplying the change in z. For v, the derivative here, it's always going to, the derivative sign is cosine, so I always get the cosine evaluated at the inside times the derivative of the inside with respect to x would be yz squared. But then for the third one, the cosine derivative of the outside evaluated the inside times the derivative of the inside with respect to y makes x z squared. And finally, the derivative with respect to z would be the cosine of xy z squared times the derivative of the inside with respect to z, which would be 2 times x times y times z. So we've got our total derivative matrix. Of course, one application would be if we had given values for x, y, and z, we could find all the rates of change at our particular location, and then we could ask, well, what if we make a small change in x, or a small change in y, or a small change in z, or some combination of those changes? How will u and v change? So we could get this this approximate error in u and v given errors or small changes in x, y, and z. But we can also get the tangent space if we have a particular location. So let's find the tangent space. Let's find the tangent space near, let's say, x equals 1, y equals 0, and z equal 2. Okay, if that's the case, then when x is 1, y is 0, and z is 2, u is going to be 1 cubed plus 0 minus 4. So 1 minus 4 is negative 3. And v, let's see, x times y times z squared is going to be 0, and the sign of 0 is 0. So to get our tangent space, then the change in u is going to be u minus minus 3. That's going to be u plus 3. And the change in v would be v minus 0. So just v. And now we can evaluate our slopes. Let's see. If x is 1, then that 3x squared is just 3, and then 1. And z is 2, so this is negative 4. Now these slopes, let's see, x, y, z squared is 0, and the cosine of 0 is 1, so in each case this is 1, and then we just have to worry about y z squared, x z squared, and so on. Let's see, y z squared, since y is 0, that's going to be 0, so we have 1 times 0, which is 0. In this middle term, though, the derivative of v with respect to y, that's 1, and then we have x times 2 squared, so 1 times 2 squared would be 4, so this derivative is 4. And here, since y is 0, we have 1 times 0, which is 0, times the changes in my inputs. So how far does x move from 1, y from 0, and z from 2? We get these two linear functions then for u and v. U is going to be 3 times x minus 1 plus y minus 4 times z minus 2, and then move this 3 over, so minus 3. And v is going to be just 4 times y, because we have 0 times x minus 1, 4 times y, and 0 times z minus 2 for v. So we get these two linear approximations. Let's see the one for u. I might be able to make it nicer. We have 3x, and we have y minus 4z. What about my constants? I have negative 3, and I have plus 8, and another negative 3. So negative 6 plus 8 would be 2. That might be a nicer way to write that. So now, this is the case where we have 3 inputs and 2 outputs. We didn't give a very good visualization for these, but we could visualize the individual functions. So here we have a nonlinear function for u, and in our particular location, this is the best linear approximation to u, or here's a nonlinear function for v, and in this given location, this is the best linear approximation for v. So we could visualize these two individually and look at them. Now, for a function with one output and three inputs like u, we generally looked at the level sets. So what we could do is we could look at the level set near u equal -3 for both the linearization and for the original function. Let's try that. I've got it set up to do in Maple here. So let's see. We have our nonlinear function, right? So we're looking at the level set where u is -3. So -3 equals x cubed plus y minus z squared. And I've chosen ranges that will include our values. And let's see, I had our linearization, except for I had a nicer way of writing it. Let's see, it was 3x plus y minus 4z plus 2. So 3x plus y minus 4z plus 2. So if we display both of those level sets together, we see there's the smooth one is the plane, right? And you can see that the plane does a really good job of approximating the nonlinear surface, at least right there in the center. That's actually where we did the linearization, where x was 1, y was 0, and z was 2. So we get a good approximation there. If we compare this nonlinear equation v equals sine x y z squared to the linearization v equals 4y, again we could look at level sets. Since these are functions with 3 inputs and one output, we could look at the level set where v is equal to 0. So we could plot 0 equals sine of x times y times z squared, and 0 equal 4y. So I set that up to do that in Maple. If we do that, we can see, okay, oops, disappeared. We get they both give this plane where y is equal to 0.